Today we're going to talk about another method of evaluating limits called L'Hopital's rule. Okay, so that's how you pronounce this, L'Hopital. And actually sometimes there's an S here too, like hospital, but it's pronounced the same. It's just two versions of the spelling for the person that made up this rule. So let's take a look then at one specific limit. Let's say the limit as x approaches 1 of x squared minus 1 over x minus 1. This is something we've looked at before in some of the other limit videos earlier in the term. And remember before, the way that we evaluated this is we first started by thinking about plugging in 1. And notice if we do that, we get this 0 over 0, which is our indeterminate form. And we noticed that we can just use algebra to basically get rid of the discontinuity at 1. Think about doing difference of squares. And then I can see that the x minus 1's cancel, and I get the limit as x approaches 1 of x plus 1. Now this is continuous, so I can just plug 1 in, and I get 2. Okay, so that's something we've looked at before. But let's do another example. Let's say I wanted to look at the limit as x approaches 1 of x to the 11th minus 2x plus 1 over 7x to the 4th minus x minus 6. Okay, so notice if I plug 1 in here, I would have 1 to the 11th, that's 1. 1 minus 2 plus 1, that would be 0. And then I'd have 7 minus 1 minus 6, that would also be 0. So similar to this one, we get an indeterminate form. But notice the algebra with this one is going to be a little bit trickier. This one was pretty straightforward because we recognized the difference of squares. This one, it might be a little bit tricky to factor. I do know that there's going to be an x minus 1 in both of these, but it would actually take long division of polynomials in order to figure out what the other part would be, so we're not going to go there. So we're going to look at another method of evaluating limits besides just using algebra, and that is, as you can expect, L'Hopital's rule. So here's what L'Hopital's rule says. Okay, so it says if the limit as x approaches a of the quotient of two functions, notice that's what we have in both of these cases, if this results in 0 over 0, like it does up here, or infinity over infinity, then the following holds. The limit as x approaches a of f of x over g of x is the same thing as the limit as x approaches a of f prime of x over g prime of x. Okay, so essentially what L'Hopital's rule says is that if we get a limit and we get a 0 over 0 or infinity over infinity, we can take the derivative of the numerator, the derivative of the denominator, and then apply the limit again, and it will be equivalent to the thing that we had started out with. Okay, so let's see if that works in this one up here that we were able to use algebra on. So I have the limit as x approaches 1, x squared minus 1 over x minus 1. So I have, again, 0 over 0, so that means I can use the L'Hopital's rule. So we're going to take the derivative of the top. The derivative of x squared minus 1 would be 2x. The derivative of x minus 1 would be 1. Now I have a continuous equation that I can plug the limit into. 2 times 1 is 2. And notice we get the same thing that we did up here. Now in this case, you know, they were both fairly straightforward and easy, but with this one, L'Hopital's rule is going to be much easier than using, trying to use algebra. Now as far as notation goes, to show my work, to show what I did from here to here, I'm going to write an LH right above the equal sign. And that just tells the reader, hey, I got 0 over 0, I'm going to use L'Hopital's, here's what I get, and now here's my limit. Okay, so let's do that for this one. Again, I see I get 0 over 0, so I'm going to say, I'm going to apply L'Hopital's rule, and I still have the limit as x approaches 1, and now we're going to take a derivative. Okay, so I have derivative of x to the 11th would be 11x to the 10th minus 2 all over 28x minus 1. Okay, so again, that's the derivative of the top, the derivative of the bottom. Now when we plug in 1, notice we no longer get indeterminate form of 0 over 0. We now get 11 minus 2, right, plugging 1 in, 1 to the 10th. 11 minus 2 would be 9, over 28 minus 1, which would be 27, and I get then an answer of 1/3. Now there is a way you could check your answer here. You could evaluate this limit numerically or graphically, and you should see answers approaching 0.333. Okay, so this opens up a lot of opportunities for us because we've gotten pretty good at taking derivatives. So we're going to be evaluating a lot more different types of limits now that we have this particular rule. Okay, so let's try another one. Let's try looking at another one that we're actually familiar with. Again, just to kind of verify L'Hopital's rule. So let's look at the limit as x approaches 0 of sine x over x. Now this is one that we've seen before, and we hopefully remember that it is 1, okay? So let's use L'Hopital's and see if we get 1 doing it that way. So notice first off that I can use L'Hopital's because if I plug in 0, I get 0 divided by 0, okay? That's the thing you should always do first to check. All right, so notice then I do get 0 over 0, so I'm going to apply L'Hopital's, and I get the limit as x approaches 0 of, the derivative of sine is cosine, derivative of x is 1, and notice now that I can simply plug 0 in because this is now a continuous at 0, and I get cosine of 0, which is 1, okay? So same thing that we had before when we went through that geometrical proof. Okay, one thing I want to point out here is kind of what this looks like visually. One thing I also want to make sure that we understand is that these two things are not equivalent. They just have equivalent limits at 0. Okay, so let me just put that as a side note here. Sine of x over x is not the same thing as cosine x over 1. Okay, so that's not what L'Hopital's is saying. It's saying that at this point, they have the same limit. Okay, so let me just, again, I'll show you that graphically. So let's think about graphing sine x over x. And if you remember from when we first investigated this limit, we have a hole at 0, and then it kind of looks like that, where this would be pi, and this would be 2 pi. That would be negative pi, negative 2 pi. Okay, and then if we look at cosine x over 1, or just cosine x, cosine of 0 is 1, so essentially it's kind of like filling that piece in, and then cosine, let's see, it would be 0 at pi over 2, so it would be negative 1 here, and you get the idea, it keeps going. But the thing I'd like to point out here again is that these two things are not the same, but they do have the same limit at 0. At 0, they both have a limit of 1. The difference is that this one is undefined at 0, or indeterminate, whereas this one is not. So we're kind of getting to that point again of almost like rewriting it at that point so that we can plug the number in. Okay, let's try some more. Okay, let's take a look at the limit as x approaches infinity of 5x cubed minus x plus 1 all over 3x cubed plus x squared minus 4. Okay, now, so we're approaching infinity here. And so let's just kind of think about what's going to happen if we think about putting in very, very large numbers for x. So the first thing I'm going to do is I'm going to raise it to the 3rd power. So think about infinity times infinity times infinity. Okay, that's going to be a really big number. I'm going to multiply by 5. It's going to make it even larger. And although I'm going to subtract infinity here, it's not as large of an infinity as what I have here, considering that I cubed it. And then I'm going to add 1, which infinity doesn't really care about. Okay, and then down here, so from here, we notice then if we essentially look at infinity, the top is going to be infinity. Okay, now if we look at the denominator, we have a very similar story in that this would be infinite, and I'm going to take away 4. It's not going to make much of a difference. So we have then essentially infinity over infinity, which, as I mentioned at the beginning, L'Hopital's rule works whether you have 0 over 0 or infinity over infinity. Let me just do a quick little side note here. These are both indeterminate form. We have talked about other indeterminate forms, like infinity minus infinity, perhaps. This is indeterminate, but L'Hopital's cannot be used here. Similarly, like 0 times infinity or 0 to the 0, those are all kind of situations where it is indeterminate, but we can't necessarily use L'Hopital's. You might be able to manipulate some things to get to that point, but we're okay here because of the fact that we have infinity over infinity, which means that we can apply L'Hopital's rule. So let's see what we end up getting when we do that. Okay, so I have L'Hopital's limit as x goes to infinity, and I'm going to take the derivative. So I have 15x squared minus 1 all over 9x squared plus 2x. Okay, so now notice if I now apply the limit, I'm still going to have infinity over infinity. Okay, so I'm still going to have the same situation that I had before. But notice that it's a little bit less severe now, at least things are in terms of squareds, so I'm going to keep going with it. So you can apply L'Hopital's rule multiple times as long as the next step still involves that indeterminate form that L'Hopital's can be used. Okay, so I still have infinity over infinity. So we are going to take the derivative again. That would be 30x over 18x plus 2. Okay, again, notice I'd still have infinity over infinity, but as you can see, if we apply it one more time, it's going to get rid of the x's. So I have derivative of 30x would be 30, derivative of this would be 18, and now I have the limit of a constant, and remember the limit of a constant is just that constant, and this simplifies to 5/3. Think about dividing everything by 6. Okay, so notice there's a little bit of a trend here, this 5/3. Notice that was actually kind of written at the very beginning, this 5/3 and this 5/3, and it's not a coincidence. If you think about what's going on here, if we're talking about infinity, if I'm going to cube infinity, then this stuff, the minus x plus 1, it's not really going to make much of a difference in the end. Similarly down here, if we're comparing to a cubed, the x squared minus 4 is not going to make much of a difference. So the end behavior of this function is really 5x cubed over 3x cubed. Let me go ahead and write that. The end behavior, again because we're talking about infinity here, the end behavior is going to be like 5x cubed over 3x cubed, and the x cubes cancel, giving me 5/3. So in these situations, you can usually kind of tell what your answer is going to be, but it's still good to go through L'Hopital's rule because that actually shows that the limit is in fact 5/3. Okay. All right, so and again, I want to point out here, this worked because of the fact that these two powers were the same. Let's just do another example really quick where we have, let's make this 5x squared minus x plus 1, 3x cubed plus x squared minus 4. Okay, so this limit's not going to come out to be 5/3 because of the fact that the denominator has a cubed in it and the numerator has a squared. So notice if I were to apply L'Hopital's, which again I can do that because this is still infinity over infinity, although the denominator infinity is larger because of the cube. But notice if I apply L'Hopital's, I get 10x minus 1, 9x squared plus 2x. Notice that's still infinity, so we can apply it again. Now I'd have 10 over 18x plus 2. Okay, now here's where we need to be careful. I cannot apply L'Hopital's rule from here because I don't have infinity over infinity anymore. The limit as x approaches infinity of 10 is 10. So I really essentially have like 10 over infinity. So if we think about this, if I take 10 over a really, really large number, that's going to be overall a really small number, right? Think about 10 divided by 1 trillion, right? And the denominator is going to be even bigger than that because it's going to infinity. So that's going to approach 0 because it's going to be approaching a really small number. So I just want to make sure we don't see this as a pattern. It only works this way because of the fact that the powers are the same, okay? that the degree of the two polynomials is the same. Okay, let's go ahead and try another example. Let's take the limit as x approaches 0 of cosine x minus 1 all over sine squared. Okay, so again, the first thing we need to do is plug in 0 to see what happens. So I know that the cosine of 0 is 1, and then I'm going to subtract 1, so I get 0 on top. And check the bottom. Sine of 0 is 0. That squared is 0. So I do have 0 over 0. And that means then that I can apply L'Hopital's rule. Okay, so let's go ahead and do that. So the derivative of cosine is negative sine, and then I have my constant, which would be 0, divided by, now let's just take a look at doing the derivative of sine squared. So there's two ways of doing this one. You can either think of it as a sine times sine and use the product rule, or I think an easier way is to think of this as sine quantity squared, which is really what it is, just rewritten differently. Okay, so here's going to be a chain rule then. My inside function is sine, my outside function is squared. So derivative of the outside, evaluated at the inside, and that's a first power, times the derivative of the inside. Derivative of sine is cosine. So writing that more simply, I get 2 sine x cosine x. Okay, so that's what's going to go up here. 2 sine x cosine x. Okay, let's go ahead and think about plugging in 0 and seeing what happens. So I have the top, I know again sine of 0 is 0, and then I'd have 2 times 0 times 1, that's still going to be 0 over 0. Now we have a few options here. I could go ahead and apply L'Hopital's rule again, okay, because again I do have that special indeterminate form where I can use L'Hopital's. But notice that I can actually do some simplification here to remove the 0 over 0. The 0 over 0 is really coming from this sine divided by sine. So notice I can just cancel those out because nothing here is being added. Everything is being multiplied. So that means then that I have the limit as x goes to 0. That would still leave a negative 1 in the numerator and a 2 cosine x in the denominator. So notice I've removed that discontinuity, and now I can just plug 0 in. I know that cosine of 0 is 1, so my answer is negative 1/2. Okay? So again, notice I didn't apply L'Hopital's here, so I didn't write it up here, because I didn't use L'Hopital's, I just used algebra. I just canceled these two out from the numerator and the denominator. So always check that after the first step. See if you can simplify things before moving on. Okay, let's just look at one more here. Limit as x approaches 0 of x squared minus 4 over x minus 2. Okay, now let's say that I'm not going to check to see if I can use L'Hopital's. I'm just going to jump right in there and use it. Okay, so if I do that, I have the limit as x approaches 0 of 2x over 1. And now I can plug in 0 and I get 0. Okay? So we have to be really careful here. Okay, let's take a look back at what we had. Notice if I plug in 0, this function is continuous at 0, right? Because if I plug in 0, I get 0 squared minus 4 over 0 minus 2, negative 4 over negative 2, that is 2. Okay, so clearly this is not actually the limit, right? So again, I just wanted to emphasize again that in order to apply L'Hopital's, you must have 0 over 0 or infinity over infinity. So your first step should always be to check if you meet that indeterminate form. And if you do, then you can apply L'Hopital's rule.